Hello everyone, welcome to In 5 Minutes. In this video, we are going to study about decimation in frequency DIF, that is radix 2 FFT. In decimation in frequency algorithm, the frequency domain sequence x of k is decimated, whereas in time domain, that is the decimation in time algorithm, the time domain sequence x of k is decimated. In this algorithm, the endpoint time domain sequence is converted to two numbers of n by 2 point sequences. Then each n by 2 point sequence is converted to two numbers of n by 4 point sequence. Thus we get 4 numbers of n by 4 point sequences, and this process is continued until we get n by 2 number of point of sequence. So here let us consider n by 2, n by 4 and sequences. So we will see that how these sequences are obtained by decimation of frequency time domain sequences. Hence this method is called as DIF. For example, let us consider frequency domain sequence x of k that can be decimated to two numbers of n by 2 point frequency, and that would be, we would call them as g1 of k and g2 of k. The g1 of k and g2 of k are the new time domain sequences that would be of g1 of n and g2 of n, whose samples are obtained from x of n. It can be shown that the endpoint DFT of x of n can be realized from two numbers of n by 2 point DFTs. Now let us prove this. Let x of n and x of k be a n point DFT pair. That would be x of n when applied to DFT, that would be x of k, and inverse DFT is applied, that would again give us x of n. Let g1 of k and g2 of k be two numbers of n by 2 point sequences obtained by the decimation of x of k. And again let g1 of k be n by 2 point DFT of g1 of n and g2 of k be n by 2 point DFT of g2 of n. Now the endpoint DFT x of k can be obtained from two numbers of n by 2 point DFTs, that is g1 of k and g2 of k. That would give us x of k when k is equal to even equal to g1 of k, and x of k when k is equal to odd g2 of k. Now we will see the proof. By definition of DFT, the endpoint DFT of x of n is given as x of k is equal to summation n is equal to 0 to capital N minus 1 x of n w raised to k n capital N. That is again equal to summation n is equal to 0 to n by 2 minus 1 x of n w raised to k n by capital N. And again modifying this term, we would get as summation n is equal to n by 2 to n minus 1 x of n wn raised to kn. What we have done here is that we have splitted the limit, that is n is equal to 0 to n minus 1. That would be n is equal to 0 to n by 2 minus 1, and again n by 2 minus 1 to capital N minus 1. If we add these both the terms, we will finally get 0 to n minus 1. Now we will solve this. That would be summation n is equal to 0 n by 2 minus 1 x of n w raised to k n capital N plus summation n is equal to 0 capital N by 2 minus 1 x of n plus capital N by 2, and again wn k n plus capital N by 2. Now here we have incremented x of n, that is x of n plus w by 2, and again n plus capital N by 2. This is capital N by 2. Now looking at the limits, the changes are here n is equal to a capital N by 2 to n minus 1. If we are incrementing n plus capital N by 2, here n by 2 minus 1 plus capital N by 2 will come out to be n minus 1. So finally this is splitted into this, that would be n plus capital N by 2. Now we are going to expand this term. It would give us summation n is equal to 0 capital N by 2 minus 1 x of n w capital N raised to k n plus summation n is equal to 0 capital N by 2 minus 1 x of n plus capital N by 2 w capital N raised to k n into w raised to k n, that is capital N by 2 into n.